Now we have Engin Kayraklioglu, sorry for saying that, from HP, and he's going to talk about locality-based optimizations in the Chapel compiler.
Thanks for the introduction, Simon. Hello, everyone. I'm Engin again, and my title of my talk is Locality-Based Optimizations in the Chapel compiler. Sorry. So Chapel's high-level features enable programmers to write their applications in a really efficient way, but at the same time, features like distributed domains, distributed arrays, or say like for all loops can enable the compiler to argue about locality and make some optimizations on that. But historically speaking, we haven't had so many optimizations that leverages that. But that's changing in the last couple of releases. And in this talk, I will talk about two optimizations that Brad also teased about in his State of the Project talk. One is automatic local access that was added in 123, and the other is automatic copy aggregation that was added in 124. So I really like this quote from Lord of the Rings. So I try to create my talk in a way that, give the necessary information for the typical Chapel users so that, they can benefit the most out of these optimizations and try to avoid pitfalls. So I will not talk too much about the implementation details or do a lot of like nitty-gritty performance analysis, but I'll just show some example codes and try to explain how the compiler thinks upon seeing such code. Let's dive right in. The first one is automatic local access. And let's see if I can get my, okay, it doesn't work, but that's okay. So here in the snippet, what you're seeing is a block distributed domain and a block distributed array. And then you have a for all that iterates over the block distributed domain while accessing the array using the loop index. So this looks innocent enough, but the distributed array access has some overheads. Every time you access index I for a distributed array, we have to check whether index I is a local index for array, for the array A. There has been some workarounds for that if this overhead becomes noticeable. One might be writing a zippered for all and using the yielded item directly, and the other might be using the local access method instead of the array access. But these are either not intuitive or just too clunky, and we don't want the user code to rely on such measures for performance. So what this optimization does is that it will its strength reduces the access to distributed arrays by avoiding that locality check if the compiler can determine the locality statically. So let's see some more examples. To begin with, we have, again, a distributed block distributed domain and two arrays on that. Let's start with a simple example and try to basically walk a mile or a yard in compiler's shoes. So upon seeing this for all loop, what the compiler will do is it will look inside the body of the for all, and it will see that there's an array access here that is underlined. That array access happens to use the same index as the loop index, that is I. So this will be a candidate for optimization. And if a for all has a candidate for optimization, the compiler will try to establish a relationship between that arrays domain and the for all's domain. So what happens next is it will try to find the declaration or how the A is created, and then it will try to see if it's kind of related to the for all's domain. And here it's kind of obvious that they are the same domain, so it would imply that A of I will be local always, and the compiler will be able to optimize this. It doesn't really have to be just a single array. You can have multiple arrays. Compiler will be able to find all the candidates, and it will be able to establish the connection for all the candidates, and it will be able to optimize. It doesn't even have to have an explicit domain as the for all domain. It can be a domain query, for example, over a distributed array. Similarly, compiler will be able to find the candidates, but this time it will see that it's a domain query. So it will try to find the relationship or the alignment relationship rather between arrays A and B, and it will be able to find that in their declaration, and it will be able to optimize this call statically. So I say statically because there are some cases where the compiler will not be able to make this sort of analysis to the end statically. Here's that example. Here we have two arrays created by the new block array helper or the factor function. And this function is nothing special for the compiler. So the compiler will not be able to establish the alignment between A and B. So what will happen for the for all body is A of I will be optimized, but B of I will not be statically optimized. But the compiler will be able to tell that this is still a good candidate for optimization. So what it will do is it will add a runtime check that will execute once per for all. And optimize B of I based on that runtime check to see whether the A.domain and B.domain are the same thing. So this has potential overheads. Of course, it's a dynamic check. It's an O1 check, not per access, but per loop checks. But there might be some overhead, I guess, if the for all is, for example, if it's too short. This causes loop cloning, which can increase compilation time. Although in real world cases, we haven't seen this become noticeable in any way. So as I said, I really want the Chapel users to be able to aware of pitfalls of this optimization so that they don't get hurt by unexpected performance. So I'll talk about pitfalls, and the first one is if you have an intervening on statement inside a for all that can change where the array access occurs, and so the compiler will not analyze the bodies of on statements inside for alls. The next is you have to use the for all index directly as the array index. Here in this example, for example, the loop index is assigned to a temporary inside the loop body, and that temporary is used as an index. The compiler will not do any data flow analysis to see if k is equal to I, even in simpler cases like this. So it needs to be the loop index explicitly. Another case is for zippered for alls, which are also common. So if you are using a zippered for all, you have to use explicit indices for all the iterands, as shown in the second line here in this box. If you are using a packed index, as shown in the first line, the compiler will not look inside the body of that for all for canons for optimization. And last but not least, if the array that you are accessing and hoping to get optimized is a for all intent, it will not be optimized. There is no like a fundamental obstacle preventing that, but there is an implementation challenge that we need to somehow find a way to optimize this. If this is a case that's really important to you, let us know so that we can prioritize working on that. Let's talk briefly about performance. So before this optimization, if you were to write stream in the way that's shown in the blue rectangle, you wouldn't get great performance. The performance of that is prior to this optimization is shown in dark blue in both plots. On the top plot, it's shown that its efficiency is about like 65% or so, as opposed to more performance idioms like the ones that are shown below that doesn't use any index access to distributed array. So these were getting near optimal efficiency. Now, thanks to this optimization, without doing any change, you can write stream-like applications just like shown in the blue rectangle, and it will perform identically to the others and get near optimal performance. So this is all about automatic local access. Let's look at the next one, which is kind of related, and it's automatic copy aggregation. Here I have another introductory snippet that is also simple, a block distributed domain, two arrays over that domain, and a for all iterating over that distributed domain. And inside of for all, we are assigning to an arrays index from another arrays index. And here the right-hand side of the assignment can be thought of as like a random access. If calculate function returns an index that happens to be remote, then this is going to cause remote access. And if this happens repeatedly, then this is fine grain, what we call fine grain communication. So every access will incur a network message. And this is a common source of overhead in PGAS languages. So what we do in Chapel world before this optimization, or still to some extent, is the use of aggregator objects. So this is, for example, what Arcuda does in similar cases. So what you have in the box below on the bottom of the slide is you have an aggregator object that is passed to the for all loop as a for all intent. as a task private variable, and inside the for all body, you call a method on that aggregator object instead of doing an actual assignment. But there are obvious drawbacks of that. First, how do you even write that aggregator? So you have to have that in an efficient implementation. And even if you have the perfect aggregator, still the end user code sort of is less expressive and it's just more code. And what this optimization does is it will rely on an analysis similar to the prior optimization, and it will try to aggregate this accesses or the assignment rather in a way that the data is moved in bulk. And in fact, what will happen under the hood is the compiler will write code that is similar to what's shown in the box, but without the user doing anything special in the code. Let's see some examples again. A simple for all loop again, and as per the previous optimization, compiler will now be able to tell that left-hand side or the destination of the copy is local. And again, with the similar analysis we do for that, it will see that this is like an array access, but likely not local. So the compiler will rewrite this for all loop under the hood to use special aggregator objects to move the data in bulk. Let's see somewhat more complicated case here. The source of the copy, it didn't really have to be source. I just did it this way. It could be either way. Here, the source of the assignment is yielded by the first iterand. It's not an array access, but it's yielded from the first iterand. And what the compiler will do here is, as per the semantics of for alls, the distribution of for all is determined by the first iterand, which implies that lowercase a will be local, and similarly, destination is likely not local, and it will be able to aggregate this. Another case is where the source is yielded by the second iterand. Here, the second iterand technically has no guarantees in terms of alignment, but the compiler will not just give up based on that, and will try to establish the relationship between the domains of the first iterand and the second iterand this time using a similar analysis. And here it's clear to us, and it will be clear to the compiler, that a.domain and a are aligned by definition, and destination is likely not local again, and it will be aggregated. Again, there are some pitfalls with this optimization as well, and this time it can even hurt performance. Let's talk about what they are. So we don't aggregate arbitrary operations yet, so it has to be a simple assignment where left-hand side and right-hand side are either yielded from the for all iterands or just a simple array access. So here, for example, right-hand side is not simple enough for the compiler to optimize today or aggregate today. Note that left-hand side A of I will be optimized for locality checks, but this will not be aggregated. We only check the last statement in the for all body because it gives us a lot of guarantees in terms of data dependencies and such. So if you have a snippet like this, only the last statement of the body will be aggregated, not the first statement, because it would require complicated alias analysis that we don't have in the compiler today. Finally, if you happen to write a code that causes aggregation to trigger, but the actual operation is fully local, it can actually hurt performance. So here in this snippet, for example, left-hand side is local and right-hand side is likely not local for the compiler. And this is enough condition for the compiler to fire aggregation. But you know as a user that, for example, get a local index function returns actually an index that happens to be local for B. So this is a case where aggregation can hurt performance. So you either do not use the aggregation flag that I will talk about in a minute, basically turn aggregation off or use it by default, or you can sort of trick the compiler. Remember the pitfall for the first optimization that I was talking about, where the index has to be the exact index of the for all index. So here, for example, in the bottom of the box, you are seeing that we are using a temporary to put I into, and then we are using that temporary as an index. So this would make the compiler think that left-hand side is not local, right-hand side is not local. I really don't know how to do remote-to-remote aggregation, so it will not aggregate for the snippet, which is what you would want in this code. Let's talk about performance briefly. So this is results and code from index gather kernel from Bale study. You can see the kernel, the straightforward kernel or elegant kernel in the green box. And if you want to optimize this with aggregator objects, as I was talking about, what you would have to do is the blue rectangle. And thanks to this optimization, you can write it in the most expressive and straightforward way, and the performance between the two will be performance of the two will be basically identical. Let me wrap it up. I talked about two optimizations: automatic local access. This is on by default. You can turn it off. You can turn the dynamic part of it off, or you can ask the compiler to be more verbose about the optimization using the flags on the slide. Next one, automatic copy aggregation. This is off by default. You can turn it on with -- auto aggregation. You can also enable verbose output using the report auto aggregation flag. And as for the future work, we want to extend the aggregation to atomic operations and likely arbitrary operations. We want to improve the worst case performance for the fully local aggregation, as I was talking about, just in case, basically. And we want to investigate extending the support for arbitrary statements in the for all and not just the last one. And with that, I'll stop here. Thank you for listening. I can answer questions now.
Thanks. Thanks, Engin, for your presentation. We have two questions now. So the first one from Anonymous. What is the loop, idiom, or analysis case that keeps you up at night? The one that feels likely to occur in real code, yet challenging to analyze, optimize?
Yeah, that's a good question. Which one should I talk about that keeps me up at night? Probably I would say like a stencil-like operation, or rather in the sense that, let me flip back in my slides a little bit. So the last box here, and you are still seeing my slides, right?
Yes.
Okay, so the final box here, for example, instead of having a function there, I can pretty much see like a simple linear function there. I don't know, for example, like I plus something or something like that, where the user would know that that kind of linear expression is going to end up being a local index, but the compiler will not be able to see that, and it will aggregate and it will hurt performance. So I think that would be the most likely scenario where that can happen. One thing that I can add here, if this line in the first for all was AI equals BI, then the compiler would not do any aggregation there because it will be able to see that the both sides are local. So that kind of an obvious or more straightforward idiom will be covered. So that's safe. But if things get just a little bit complicated, it starts to get scary for me.
Okay, we have another question from Anonymous. In which release were these optimizations introduced?
The first one was 123, the local access one. The copy aggregation was introduced in 124.
Thanks. Now from Akiro Ayashi, he says, great work, Engin. For the Bale benchmark results, have you compared the chapel with auto aggregation number with the original conveyor library with UPC or Shemin?
Yeah, that's not something that I have did. I just did the compiler optimization, but Elliot, if you're there, do you want to chime in on that? I think you would have the answer.
Yeah, so we have done comparisons to the reference Bale, and generally speaking, we're on par with Bale Xstack, which is kind of the older implementation of aggregators. And then we're actually ahead of conveyors for idioms like index gather, where kind of the more simplistic Xstack or kind of our aggregators can outperform it. But yeah, in general, performance is competitive with the optimized UPC and SHMEM versions.
Okay, another question from Nikhil Padmanabhan. Chapel has largely stayed away from user-facing pragmas. While I think this is largely great, any thoughts about adding these for fine-grained control?
Yeah, that's a good question. I think Nikhil is referring to, for example, being able to disable aggregation for some specific statement and such. And that would be something that we are discussing, but we don't have like internal consensus, if you will, as to how it how we can do that in a nice manner. I think some of the context that it came up is sort of like having something like a local block that can say that can specify some properties of a arbitrary block in code that in which you can assure compiler to do something special, or thwart compiler to do something special. This might happen in the context of, I guess, context managers that are coming up in the next couple of releases. You might say that there is no aggregation in this block, and the compiler will just not do any aggregation. So I don't know about pragmas, whether we want something like that in the language, but that's just kind of me personally spitballing an answer here. As a general kind of direction, maybe Brad can have, might have more to say there. Maybe he's not on.
You caught me advertising the next session. I'm sorry, I missed that.
No, that's okay. I was just talking about maybe adding pragmas or annotations, some sort of that would disable compiler optimizations or basically control it. I think that's something that we've been discussing.
Yeah, so I think the closest we've talked about there is we've been talking for a while now about some sort of annotation-based capability in Chapel that could be used to express information that wouldn't alter the semantics of the program necessarily, but would give the compiler more information. I think that could be a tool for use here. I don't know if I have much more to say about that at this point.
Thanks.
I know we are in the break, but I have a question.
Sure.
For your presentation, if I can, without passing like Slido. Well, you know CHIUW because you helped us programming. So we're often using subdomains from a main domain that was used to allocate memory in our loops. So I'm not sure if you mentioned it, but are you gonna add some locality-based optimization for using subdomains? Oh yeah. Here.
So this was in my backup slides. It's kind of something that I gleaned over. So domains doesn't really have to be exactly identical for optimization. So compiler will add dynamic checks for such cases, but it does more kind of a relaxed check for domain alignment, basically. And if you are doing an iteration over a local subdomain, for example, it is technically aligned with the parent subdomain, the parent domain. So the checks on the optimization will occur for those cases as well. But I think one thing maybe specific for CHIUW is like this is still limited to for alls. So if you have a for loop, it will not work. It's just for alls.
Yeah, we saw that we still need to use a lot of local blocks to limit, to improve a bit the performances.
Right. We hopefully want to avoid that.
Yeah, I know. Okay, I think it completes the session one. So I'd like to thank the three presenters we had, also all the attendees and people who asked great questions.